Fantastic. Well, good morning, everyone, and thanks very much for coming. It's lovely again to see such a huge crowd here today. I'm Mark Nicholson. I'm one of the founders and the CEO of Vivacity, and I wanted to talk to you today about Project PROACT, which is a DFT and GDS funded program to start to explore how we can make control rooms more proactive rather than reactive. So, agenda that I want to go through. To explain a bit more of what I really mean by proactivity versus reactivity in a traffic control center. I want to talk a bit about some of the solutions to that around better data sets and then better alerting systems. I want to talk a little bit about how COVID impacted the project. And then I want to explore where do we go from here? What's the technology landscape to take this even further? So kicking off with the problem, the challenge that we were trying to address. So if you take a traffic control center today, they typically take in a huge number of data feeds and then feed that out into a huge number of different systems. So this might include reading data from CCTV, looking at Google Maps, taking calls from the emergency services or even members of the public. So they're trying to parse all these different data sets and then take those out in terms of changing traffic signal control timings, in terms of putting up new signs on VMS, in terms of sending out messages to people over things like Twitter. There's a lot of different data inputs and a lot of different data outputs. And in order to do that, the people in the middle are start multitasking, trying to manage all these different varied inputs and outputs all at the same time in a very time-pressured environment. We all know that the longer you delay trying to act on a problem on the roads, the worse it gets. So you've got this pressure cooker situation of people trying to deal with a huge number of different inputs and outputs in a very short period of time. And that's what I describe as the reactive control room. They are trying to just react to presence of things on the road and make rapid changes in this time-pressured environment. And this is true across a wide range of different cities, whether that's smaller cities with just a single-person team or a small team at any one time, all the way up to the other end of the spectrum with sort of huge 30-person teams managing those road networks. Even at all these different scales, got the same problem. It's always still reactive, looking at the city network and trying to work out how do we react to the challenges that are happening live within that network. So to zoom in on the particular example that we were using in this case, which is over in Bournemouth, Christchurch and Poole, there's a junction just outside the hospital where traffic typically builds up. This traffic gets inevitably particularly bad when there's an incident on that road, and that causes problems for the hospital, partly on the ambulance side, but actually primarily on the car park side. People trying to leave at sort of visiting hours, and the road there becomes incredibly congested. People cannot exit the hospital. And so that level of congestion causes complaints back to the council. It causes challenges for managing that local road network. So the goal of this project was to solve this particular problem, or at least provide some partial solutions to it, and provide a broader solution that would apply across many other authorities across the country. So what does that solution actually need to look like? We identified 3 key areas that we needed to act on. First, we needed to give better live data sets. Today, those CCTV feeds are incredibly manual. Someone has to spend huge amounts of time trying to trawl through, working out what's happening. So better live data sets to work out what's going on. We need to provide much better diagnoses of the challenges. The control center knows that when there is an issue in this particular part of the city, then it's the car parks that are impacted. But how do you get to know exactly where you should solve that problem? How do you make sure that when an alert comes in, it's the right problem that you're solving in the first place? And finally, the actual solution bit. When the control center then wants to do something with that data, they need to go through a range of different programs to actually implement their solution. How do we make it much easier for them to deploy a solution into the real world? And that's what we mean by a proactive control center, trying to get to a world where they have much better data sets, where that is much more accessible. You automatically diagnose, you automatically solve as much as you can. So what solution were we suggesting to this challenge? Firstly, it's based on better data sets. So a number of you might have seen this video before. This is one of the core products of Vivacity, which is computer vision powered sensor to really understand what's happening on the road in much more detail. So it starts off gathering path data. You can see the paths of all the different road users, looking then about the count, classification and count of those different road users across a number of different parts of the road network, looking at how many are going down the cycle lanes or on the pavements or on the side roads indeed. Then starting to get more interesting for this particular use case, looking at occupancy. So by that, I don't mean vehicle occupancy, I mean zonal occupancy. How many people are queuing in an area on the road? A queue is very poorly defined. So from a more technical point of view, we've taken the word occupancy to look at how many vehicles are in a given area. You can get turning movements from these cameras. You can gather speed data from the paths of the different vehicles. We have ANPR built in, so we get journey time. That ANPR gives us origin destination as well. Point being, there's a huge range of data sets that we get from these cameras, and that has been the basis of this project, is using that data, feeding that data into the control center and seeing what can be done with it. So first starting point, huge range of data sets in order to understand what's going on. How do you actually define a congestion problem from those data sets? From a technology point of view, where do you draw the lines on what congestion is? Because if you look at current solutions, technologies, CCTV, it's very manual, just looking at it and just going, okay, yeah, that's a queue, that's an abnormal queue, that's a congested queue. From looking at Google Maps, sure, Google Maps will define you a level of congestion, but that's all very, it's very finger in the air. It's a very gut feel level, which doesn't necessarily translate to what a traffic engineer would call congestion. So we've defined it in 3 different ways. Firstly, looking at the occupancy piece. So how many vehicles are in particular areas? How dense are those queues that are building up? Second is the speed, particularly by reference to the normal speed on that bit of road. You'd always expect speeds to be slower by traffic signals, for example, but how do these speeds compare to what is normal? And finally, journey time. Journey time data coming from these sensors, much like from the likes of Google, can be used to pretty accurately define a level of congestion in an area, but when combined with the occupancy and speed, really zoom in to a very granular and micro definition of congestion. So using all these different data sets to derive insights about when congestion is happening within that road network. So understanding when congestion is happening is the first step. Actually alerting the control center operatives to say, this is an issue right here, right now, is the next step. So those alerts and the definition of those alerts is quite an important part of the program. Now, in principle, you can draw some manual lines to say, okay, if the journey time on this particular route goes over 2 minutes, then that is congested, for example. Actually, what you find in practice is that kind of approach becomes extremely challenging at scale. On this pretty small area of the BCP Council, we had 19 sensors. Each sensor was providing 5 different data feeds into this project. You're interested then in defining congestion, perhaps morning peak, into peak and off peak. You've then got weekdays and weekends. You've got to try to define an upper and lower limit. And suddenly you're asking the council to define 1,000 different limits on what they call congestion. That is clearly untenable. You can't ask an authority to go through to that level of detail to try to define those. So manual calibration is kind of out from the point of view of looking at congestion. Instead, we used an approach of looking at dynamic historic averages, so looking at a rolling average over the last few weeks to say, how busy was this area, and is what's happening today abnormal? And that's fundamentally what this all comes down to. We want to alert the authorities to abnormal behavior. We want to avoid false alerts. We want to avoid something going off at 4:30 every day because, surprise, surprise, it's peak hour traffic. We want to say, this is something unusual. This is something you actually need to react to. So adding in a rolling average gave us that historical ability. You need to then have a level of configurable limits so that the authority can say, I want to react to a once a week problem, or a once a month problem, or a once a year problem. So you need to be able to configure those limits to give that sort of that input to what you call a false positive versus a real alert. You need to automatically adapt to what's going on. Again, this comes back to the rolling averages to make sure that as traffic networks change, as, for example, the impact of COVID that we were just talking about settles into the road network, then we can adapt to those changes and say, this is abnormal even in this new world, rather than just abnormal versus where we calibrated things to before. The next step with this would be to use machine learning and to actually say, I want to tell an algorithm just to show me the abnormal events. I don't want to try to calibrate that in any way. I just want to ask the algorithm to do it all for me. Now, this is the kind of technology that you need to have done a lot of deployments elsewhere. You need to have rolled out the sort of dynamic historic averages type approach elsewhere in order to train bigger machine learning. So in this project, we didn't go that far. That would be a next step as these kinds of systems become more commonplace. What do we then do with the alerts? So those alerts went into texts, so went straight to the operatives to say, this is what's actually happening on the roads right now, and alerting them in real time to those problems. They also went into a centralized dashboard. So that then allows people to say, okay, I've got a text, this is an area that I'm worried about, I'm going to go look into this in more detail and understand what that looked like. With that dashboard, there was the ability to view images from these sensors. So crucially, blurred images to make sure that they're all compliant with GDPR, but blurred images that are live are enough to understand, is there a traffic jam there? You can then look through that camera and say, okay, is there an issue? It's the equivalent of CCTV, but the system is all tied together. You don't have to switch to a different system to look at your camera, work out exactly where that alert was, bring up the right camera. It's all built into the same thing. And crucially, this is actually then a much cheaper solution than CCTV. You don't need to roll out a network of sensors and a network of CCTV side by side. You can just do the single network. So this set of live blurred images is one critical part of diagnosing the issue on the roads. Second crucial part is providing a broader data set about what's happening. Just outlines the wide range of different data types that sensors produce. All of those data types were then available to look at if there was a particular issue, zoom in, let's look at journey times, let's look at occupancy, let's look at speeds, and really try to dig down into those challenges. So finally, as you start to get to the fix stage of the problem, you've worked out there's an action, then want to go through and implement that in one of the wide range of different parts of the ecosystem. This actually already exists. There was no point in this project in us trying to reproduce that. So we're working with Unix in order to work with the Stratos UTMC. Apologies, I wrote this before the name change. So looking at then different parts of that ecosystem, different user management, making sure that then fed into the strategy manager. And then that was actually what produced text alerts that I talked about before. So making sure that we're integrating with the existing systems rather than trying to replace them wholesale, just fixing the problems where they're not already solved. For those who are interested in what's happening behind the scenes, there was a WebSocket server which fed into the Siemens backend systems. Happy to talk about that more afterwards. And in terms of the progression of this technology, we started off with the texts and then sending out messages onto the VMS. The next stage is then to look at actually changing the signal timing automatically. I think in order to do that, you need to have a lot of confidence in the system. So that was something that we were working up to over the course of the program. Wanted to highlight a couple of the challenges that we encountered in this project, particularly around COVID, which I think definitely brought some benefits as well as some interesting challenges to the project. I think the benefit side, we saw that actually as a result of this program, we'd unlocked the ability to manage traffic much better from home. And so suddenly we're in a world where the authority had access to the cloud systems to look at all the images on the road. They didn't need to be in the control center to look at CCTV. They had access to all this data from their laptops at home. The text was still live, still going back to them. So actually we're in a position where we'd virtualize the control center. And I think that is an interesting transition for authorities to make in a world where we're all trying to work from home more, to get to a world where it's much easier to manage from home. So fully remote traffic management through these kinds of alerting and visual data systems. The other thing that I wanted to talk about with COVID was new data sets being provided. I'm sure many of you have already seen the classic curves of what happens in COVID. I'm not going to re-show those. I'm going to show one of the most interesting graphs that I've seen from the COVID side of things, which was looking primarily at social distancing. So what you're seeing here are in different areas. So far left is city centre, then local centres into residential, and then far right going into canals, looking at social distancing in those areas and how people were behaving. So where something is to the left of the line, that's saying there is less interaction at that distance. To the right of the line is saying there's more interaction. So what we're seeing is in the city centres, when COVID hit, people were trying to stay further apart. There was less interaction at the kind of less than 1 or 2 metre level. Whereas as you go to the canals on the far right, you actually saw much more interaction really close together at 1 metre or 2 apart, because the canal and towpaths are so narrow. They were really, really busy in those times. So we saw a huge number of people trying to get out of their houses, going to the canals, and then getting really close together as a result of that. So this kind of data was an interesting sort of outcome from A, COVID, and B, from these sensors. Just like to say thank you to the DFT for their work with us on the COVID data. I think it was really, really exciting to be able to feed some of this into the national methods. So coming back to the project then, what did we actually do as a result of this? How can we summarize where we got to? We provided these series of live data sets, particularly occupancy, speed, and journey times from these sensors. We gave all those into a dynamic alerting system, which fed them through into diagnosis capabilities, giving these live images from every sensor, and then allowing the control center operatives to go back into the live data as well, all of this being available everywhere. That gave a situational understanding, which allowed us to feed back into Stratos to make changes to the road networks, whether that was putting up signs on VMS to divert people around the problem area, whether that was trying to hold people a bit further back in the traffic signal system in order to avoid them hitting this particular problem junction. So within the project, we've demonstrated this whole pipeline and proved that the alerting and live data did make a genuine difference to the way the authority was managing things. Now, there is a next step beyond that in terms of how you can solve this problem, thinking about signal control. So I want to talk briefly about this. It's slightly beyond the scope of Project PROACT itself, but just how can you then feed some of this data and capability into signal control in order to make a better outcome. So currently, we have these congestion alerts going into UTMC and then largely activating one of a number of predefined control plans to say, we're going to act this way in order to mitigate this particular challenge on the network. And that requires a lot of effort to predefine those control plans. They're never perfectly aligned to what's happening. They're sort of bucketing things together to try to say, okay, this is a group of scenarios in which we might behave in a certain way. The project that we've been doing elsewhere in Manchester looks at how we can use AI in order to control the signals themselves to react to these kinds of challenges. So how can you adapt much more dynamically using AI rather than trying to change fixed time manually or input things into Scoot? So what actually is this system? It uses very similar kinds of data sets to what I was just talking about from the sensors, but crucially feeds those data sets into traffic microsimulation. So we get an incredibly well-calibrated simulation from all the data that we're gathering. We then run many thousands of those simulations in order to train our AI on how to control the traffic signals. So that AI is then learning fundamentally by trial and error, by mistakes, in order to work out, given a particular scenario, how do I optimize the traffic most effectively for that scenario? That then gave us AI, which we deployed in the real world, first in Manchester, and more recently in Cambridge and Peterborough as well, in order to say, how well can AI control traffic, given this huge amount of data that's coming in, given the microsims that underpin that. What we found versus a Scoot junction was that we could reduce the average journey time by 23%. I'm just going to let that sink in for a second. 23% reductions in journey time. This was over an A/B trial over a couple of months. compare that to what Scoot does versus VA, for example, which is typically seen as between 10 and 15%. We were 23% better again than Scoot. So dramatic reductions in journey times in this region as a result of using AI to control the traffic signals. Now, this isn't normally the subject of my talk, so I'm going to stop talking about it there. Happy to take questions about it or chat to people afterwards. But that is the end of the presentation. I'm relatively early, so I think we've got a fair bit of time for questions now. But thank you very much for listening.
Okay.
You want this?
Yeah, I think
I have one each, if you want.
Exactly.
I can give you a second.
well, good heavens above, technology races ahead here. We're going to have two microphones. In the sweepstakes, I'm going to call the lectern over. Is double the jump.
I was trying not to stand on the lead, though. That would help.
Possibly in different directions at once. Anyway, so click that on. And I have a question, but that's me stealing the floor. Do we have any thoughts or questions people had out in the audience? If not immediately, first one I had was, let's go back to that hospital car parking pool.
Sure.
So you took us through the steps, you showed us, saw what was really happening with the traffic, you saw the traffic build up, you sent a message, somebody did something. Did it work?
So I think the crucial thing here is that the solutions to this have been proven in terms of how to actually react to this. It's something that BCP has been dealing with for a long time. The challenge is how can we get to it more quickly, and how can we actually react to those challenges sort of in the moment, rather than waiting for a problem to build up, waiting for someone to notice it, and then coming back to enact the pre-existing control plans. So for us, it's all about getting ahead of the problem. Michelle, I don't know if you want to comment on this at all.
Yeah, one of the big problems we have in the area where it was deployed is that it's very reactive. But the main hospital there, which has got hundreds of parking spaces, it's also now part of Wessex. Now, because we're on the border with Christchurch and it's a river crossing, 3 lanes merge, a single lane go over to Christchurch. So the slightest thing that happens in Christchurch have a knock-on effect to the system. What we were finding is that we're finding out the problems. We're not glued to the day job as well. And by the time a member of staff might be going through, and people say, "Oh, are you aware?" Now that's a 2-mile sort of distance. So by the time we've gone in to have a look, car park can't, nothing can get out onto the carriageway at all. All of the space fills up between our roundabout trying to get to Christchurch. Now what we wanted to do was we changed things in Wessex fields manually. We actually made more space so we could tell them, don't sit there, you're trying to turn back. You're not going anywhere for hours. One of the big problems we had is we had cancer patients. We had their treatment going to the car and they were spending 2.5 hours trying to get out, which was a major problem. So doing this, we get an alert and you're surprised how nice it is to see an alert and just smile. You know, you don't need to know that, but it's nice. But with it coming in saying suggestion, we can have a look at all the photographs. We can then alert the hospital and Wessex Fields so that the staff from all of the area know, don't go to the left, and change signals, fire everybody out to the right, and take them up around the back.
Thank you. Much better expressed than I could.
So for those who couldn't hear this perhaps on the broadcast, the answer to my question was yes, it worked, which is thumbs up from me, the road user. That's excellent. So another thought again from me. So please do fire in if there are thoughts or questions here. Can I ask? Well, I think I might just follow on to that, which is we're talking about an individual junction, we're talking about an individual site, but most of these guys are, as you said, they're either trying to manage a town, city, or really complicated city. Is this all scalable so that it could deal with the sort of complexities? I mean, even probably the city of York is not that big on the grand scale of things, but it's still pretty big. You've got a lot of monitoring, a lot of roads, a lot of traffic. Is it scalable?
So I suppose the point of this is to try to increase the scalability of traffic control in general. It's much less scalable to have a group of people trying to look at CCTV across the city and try to assimilate all of that information than it is to have some kind of AI system go through that for you and say, okay, these are the interesting bits, look here. So we're trying to increase that scalability. You're right that it still becomes difficult at a large scale. And that's where I think the AI needs to become ever more sophisticated to provide a lot of that sort of fixing solutions rather than just alerting solutions. And I think as an industry, we're on that journey to try to solve that.
Now, one of the things that we're finding is that because we want to expand slightly with our VMS and signal timing, if we get, say, a bus broken down, which is now starting to have a knock effect, then we know all the traffic and force through to the section. When we write a strategy, that deals with that thing of what can happen if someone's backward or busy, and then maybe something that's there. So the initial strategy will now no longer is good, but another situation. It's trying to work out got a strategy for this. If this happens, we have to change the strategy for that. So it's like building sort of one after the other. By having the alert early, we can hopefully be engaged, see what's going on. It is a learning. So as we do that, we're going to see how hopefully we will work out what needs to be done. But automation is great when no traffic behaves in a rather random place sometimes. You know, you can set it up and say, I want to go this way, and you've still got Mr. Smith, I'm going this way. Can't get away.
Yeah, I find I have a tremendous desire to argue with the sat nav. I know where I'm going. But it feels like, so getting ahead of the game, getting the early alert, thinking through what you can do, all sounds great. I wonder to what extent when you're thinking things through, you're thinking of the what if scenarios, whereas what you're describing really is a learned experience. So AI built on, this is what happened last time I did this, this is what happened last time I did that. Does your system have any sense of, I wonder what would happen if I did the other?
So I think this is a long-running challenge with AI, is that it can only learn from the experiences it's had. And so it needs to have seen things before for AI to be able to work well. Having said that, simulation gives you the ability to show all of those scenarios that aren't very common, but that you can occasionally explore. And so I think from my perspective, this is about combining AI and simulation systems to get to a world where you can solve all of this together. So you learn from the real world experience where you learn from the simulation experience, perhaps first. So simulation first to run 1,000 scenarios to see what happens in all of those, to train the AI on that. It then adapts better from the real world and sort of learns, okay, how do I then make minor changes where the simulation wasn't quite perfect, and I need to adapt something better. And then as you get ever more sophisticated, you then start to run the simulations on the extremely niche scenarios that last Tuesday you saw 3 things conflate together, and suddenly you need to work out how to deal with that. You might run a specific simulation on that and train the AI in that world. So I think it's about going through a journey which involves a combination of AI and simulation playing off each other.
Thank you. And I can see a hand has gone up there, sir. I didn't hear that.
So this is about the way that the system adapts to bank holidays and school holidays and these slightly less common types of days. So I suppose, again, this is a question of going how far down that sort of AI journey you go. So I think in this particular case, we hadn't gone too far down that and we hadn't sort of properly adapted to that. But I think the next stage is to say, okay, if we're typically reacting to the last 3 weeks of historic averages, actually, why don't we react to the last 21 bank holidays instead? And so I think there are ways of trying to categorize different days, group them together. But as I say, as you start to get into an AI world, you feed that in as part of the system and it learns to adapt to both what's happening in the last 3 weeks and the fact it's bank holiday adds that in as an extra parameter essentially, and then you get to a better outcome. So you're right, it adds a layer of complexity to deal with it.
Thank you. Potentially a last one from me. If the tea and coffees are ready, which we are going to check, we might break early because we've only allowed 10 minutes, but that was when we thought there'd be only enough people to fill the tables. So might go slightly early, but I'm just wondering. Oh, sorry, I didn't see a hand going up there. Yes. Yeah.
In London, over the last sort of 10, 20 years, been obsessed with the network. We wanted to get to a situation where we drive and there wasn't to say like 50% of you stay where you are, 25% of you divert to 25%. We've not really got to that stage yet. Would you see your project sort of leading up to something like that, where you could communicate individual drivers when there wasn't, say to some of them, stay where you are, like the gentleman said earlier about holding your nerve, stay where you are, better. It's better for the network, 50% be stable. Would you see that as a sort of incremental stage? Sure.
So just to reiterate the questions about how does this all evolve as you're trying to redirect vehicles themselves, how does that link into this challenge? So I think from my perspective, it is all related. I think there is a whole spectrum of opportunities here to try to solve with this kind of technology. This is very much the first step. Let's give data back to the people in the control center who can react best to it and who are the sort of sophisticated professional users of that data. To get that to the point where you can send it out to JVlogs on the streets, I think is then sort of, you need to be at that next level of sophistication. You can't give them false alerts because the moment they get a false alert, they will stop trusting the system. There is no faith there. So you need to be extremely good every time. You need to build up that comms capability, which is not trivial, to interface that with sat navs, with next vehicles, with autonomous vehicles. I think there's probably a whole company in there in the future to actually solve that particular problem. So there are a number of pieces of the puzzle that you need to get there. But I agree that ultimately you want to get to a world where you can redirect vehicles across the network. And this is a first step of saying, okay, we now automatically know where there is a problem and can start to automatically suggest solutions to that. That is then first stages on that journey.
And I guess that the part of the challenge getting along that journey would be if I've already got a proprietary sat nav, do I believe you or do I stick with whatever the sat nav is saying, or does your system connect with the sat nav providers so that the same artificial intelligence solution is coming through whichever channel I look at? This is fascinating. Andy, I think you were going to say that chip in about how we get messages change some stuff. Well, that's something I've been very keen on. And I know something that National Highways, aka Highways England, Highways Agency, have been playing with for some time. So we'll look forward to that. I think that's a nice segue, actually. We've checked, the tea and coffee is there. So I think, with no further ado, I'm going to say thanks. That was absolutely fascinating. Thank you for coming.